Okay, so we've heard a lot about NEID and other instruments today, and Paul Robertson's talk, and actually Doug Hudgens, and now BJ have set this up really well for me. When I was creating this talk, I was cognizant of the fact that it's 5:30 on the first day, and I originally had a whole bunch of block diagrams talking about pipeline architecture, and then I decided that that was probably a bad idea. So I took them out. And instead, I'm gonna kind of talk a little philosophically about pipeline development. The NEID pipeline has been in development now for close to 5 years, and it works quite well. And I want to talk about some lessons that we've learned. But first, 4 years ago in Grindelwald, I gave a talk about pipelines, mostly based on the experience that we had developing the HPF pipeline, which was working at that point, and a hypothetical NEID pipeline, which didn't exist yet. And if I can go forward here. And I gave this slide, which I found yesterday. And it turns out to have been apt with our NEID experience. This is hard, and the software is hard, and the hardware is hard, and it's all pretty hard. This has taken a lot of people. The pipeline effort in NEID is a funded effort. It has been from the very beginning. It's a well-funded effort, and we've had a large team with people rotating through. We have 2 new team members, Daniel Krolikowski and Leonardo Paredes, who are both here at the meeting this week, new postdocs at Arizona, who are going to take the pipeline into the next step. But just a huge number of people working on the software itself, and then also on running the software, interacting with PIs who are trying to use the data, and et cetera, et cetera. So some of the questions that I was thinking about as I was writing this, I think are important for people to keep in mind when you're generating a pipeline, when you're thinking about a pipeline. And they're basically, what are the requirements for the pipeline, and how do we go about meeting those requirements? So data consistency, data formats, BJ was just talking about this, they should be thought out well from the beginning. And we did that extensively with the NEID pipeline. We didn't get everything right. You also have to think about, well, what if we want to add a new feature to the pipeline, or a new feature to the data product? Does putting that in break the existing archive? We had this problem a year ago with some of our exposure meter data, adding it in, something we'd overlooked originally, and it was going to break the NextI archive. And we had to figure out how to get around that. Who will be running the pipeline? We don't run our own pipeline. Our pipeline is run at TAC, at the Texas Advanced Center for Computing. And so they are not experts at understanding error messages that may come out of the pipeline, which means that we have to both iterate with them and think about when we developed it, how that was going to work. Hardware requirements, I don't mean spectrograph hardware, I mean computer hardware. This has been a problem that I didn't anticipate, but these spectrographs last a long time. Computer high-performance clusters do not. They have a short life that is measured in months to years. They change architecture every time based on whatever was cheapest or they got the best deal on. CPU architecture, memory architecture, disk I/O. This has been a big problem, making sure that things run consistently from version to version over time when spun up on different computers. What data do you need to process it? We've heard a talk a couple of talks ago about what you can do with solar data if you have all of the data in front of you. But most of these pipelines, at least the NEID pipeline, certainly in the HPF pipeline as well, don't have access to all the data. They have access to a chunk of the data. And so that limits what you can do. You can't do a template matching RV approach if all you have is one epoch of your data. It doesn't work. Ensuring continuity of knowledge across generations of developers. We've had postdocs and graduate students meaningfully contribute to the pipeline who are no longer actively involved. And despite the best of intentions, if I have to ask them a question about how something works, I'm essentially asking them to volunteer, which sometimes works really well, and sometimes they're just stretched too thin. And then the last thing BJ was touching about this with the questions from Francesco, how do you know what's happening with your instrument? Problems in the hardware often show up in the data analysis before you realize that there's a problem in the hardware. So you've got to have that loop running. So I'm going to speed up here a little bit. NEID takes data on about 70% of the nights the wind nights. This is a combination of in and explore time and wind partner time. 70% is close enough to 1. We are essentially on the telescope running the pipeline every night. We take solar data every day. We take calibrations every day. And most of this has been automated except for the nighttime observations. We also have had 3 different startups of the instrument, which Paul talked about. I don't need to go into them, but that definitely screws up your pipeline development, and it's caused problems with ours. The pipeline, as BJ said, takes our raw level 0 data, it turns it into derived products. We do this looking only at a set of data from that run. So a run is calibrations, science data, calibrations. So for nighttime, it's evening cals, nighttime data, morning cals, and the vice versa for solar data. We've got the pipeline running on multiple different clusters at TAC, at Arizona, at AWS, and that's been a bit of a challenge, but it does work. We've had some interesting algorithmic problems that we've had to tackle. Our grading, as many of you have heard, is not the best, has some issues, and the consequence of this is we have a significant scattered light problem between the fibers. It's about an order of magnitude larger than we anticipated when we designed the cross dispersion and the fiber spacing. This was a big problem that has to be dealt with in the pipeline. We also have a contamination issue on the detector that also has to be dealt with some very sophisticated flat fielding. So these things were not anticipated from the beginning, and these fall into the, if you can fix it in hardware, that's great, but otherwise you'll spend a lot of time fixing it in software. The wavelength solution, we've heard a lot of talk about thorium and laser combs. We use a combination of thorium, Etalon, and laser comb data to calibrate our very, very wide bandpass. The laser comb is a primary calibrator, but it only works down to about 5,000 angstroms. The thorium solution provides the baseline wavelength solution. We reset the 0 point of that at the beginning of every night with the laser comb, and then we use the Etalon to measure the drift throughout the night. The instrument drifts about 2 meters per second over the night, and then it resets itself the next day, and that's tied to the LN2 fill that's causing very, very small physical motions inside the instrument. I'm going to skip over the data products in the interest of time, but our data products mirror those of KPF. Actually, I think it's the other way around. There's a lot of personnel crossover between the two software teams there. But level 0 is what's produced on the mountain and sent to the Nexi archive and then off to TAC to be processed. Level 1 and level 2, please don't try and read these. If you care about what's in the individual boxes, I screenshot these right off our documentation, which is available on the IPAC website. Level 1 is essentially wavelength calibrated, extracted spectra for every order with variances that are properly tracked through the extraction. Level 2 is that information plus the derived products like radial velocities from a CCF, a telluric model, activity indicators, ancillary products like that. The reason we have 2 different products is because level 1 still exists for all of the calibration data, but it does not exist, or level 1 only exists for the calibration data. Level 2 only exists for the nighttime data. We can't make level 2 data out of cals. There's no RV to be measured. So a week and a half ago, I was at the Flatiron Institute for the Sun as a Star workshop, and I had a realization talking with people there that many people don't know how to get our data. A lot of NEID data is public, very, very public. It exists on an IPAC website. You can go, you can type in your target, or you can go, there's a special page for the solar observations. It is all downloadable. The standard stars are downloadable. The only things that are proprietary are the GTO program, and if you have a GEO program, that has an 18-month proprietary period, I think, attached to it. You can see not only a roll-up of the data, but also you can generate a nice plot using functionality that BJ worked on that shows the roll-up RVs. So it's a quick look RV, essentially, with the actual RVs. We have documentation that's very similar to the KPF documentation, also using Sphinx. If you've got a question about algorithms, I encourage you to look at the documentation first. If you still have a question about algorithms, please reach out to me. Doug Hajin showed this plot, but in a much smaller format in his talk. This is the RV performance of NEID using the DRP velocities over that first chunk of science run leading up to the June fire. This plot was produced by Sam Halvertson. He and I iterated on it back over the summer while we were waiting to be able to restart the mountain. The performance is quite good. We have 2 stars, Tau Ceti and Sigma Draconis, that are at the 70 centimeter per second level. We have not done a lot of cleaning of this data. There's minimal cleaning. It's basically the RVs coming out of the pipeline. We have a versioning scheme that has confused people, so I just thought I would mention it briefly. We're using a very traditional major minor point version release. We're up to 1.2.1, I think, as of last week. The minor versions should be treated as discrete, distinct objects and not co-mixed. The point versions can be co-mixed. And if you've got questions about that or anything else, I encourage you to reach out to NECSI. There's a help email on the website, or send me an email directly, and I'll try to help. And I think with that, I'll just leave this this summary slide up, which is those 2 pages that I had earlier, but in a much smaller font format. So.
Very good. Thank you, Chad. Let's give Chad a round of applause. Okay, questions from the audience. Sharon has one. Ben's going to bring you a microphone in just a moment.
Hey, Chad, great talk. I'm confused when you say that the HARPS team has, access to all their data and they can use a source of like solar observations and observations on every star to reduce the velocity. You said you only have access to blocks of data. I understand data belong to individual PIs, but don't you guys have access to everything?
Right. So what I mean by that is it's a fundamental architecture question in how the pipeline runs. When our pipeline runs, it was designed behind a requirement that says the pipeline only needs to look at the data that it's processing for that daytime run, for example. So for a solar run, when we do a solar run, we send the morning cals, the solar data from that day, the evening cals. And the pipeline has to run on just that set of data, and it's not allowed to look at other data. And this is mostly a data transfer and storage problem. Right now, the NEID instrument has taken about 65 terabytes of raw data. This is not a huge amount, but it's also not a trivial amount to be moving back and forth and staging on fast disks. We have about 15 terabytes of processed solar data. It's 140,000 solar spectra so far. So in principle, there's a lot to be gained here by taking a holistic approach and looking at all of that data. And I encourage people to do that, but the pipeline doesn't do it by design.
Okay, thanks.
Other questions in the room? We have time for one more. Oh, Francesco, go right ahead.
You mentioned something about the combination of the laser frequency comb with the Fabry-Perot and the thorium, and I got confused. So you don't use the Fabry-Perot to extend?
We do.
Ah, okay.
Yeah. So the thorium sets the base solution, and then the laser comb gives us our 0 point. The Fabry-Perot gives us down to 4,000 angstroms, and it's a fairly complicated bootstrap across that. But over the night, the Fabry-Perot is what carries us over the night that we measure the drift. Yeah.
Okay, thank you.
Okay, let's thank